Okay, Assalamu alaikum. Today we want to talk about chapter 16, carbohydrates. And we will cover some of these uh, sections in this lecture and in coming lectures. And the first section is sugars, their structures and stereochemistry. Now, carbohydrates are one of the four types of biomolecules, and they are polyhydroxyaldehydes or polyhydroxyketones or compounds that can be hydrolyzed to them. Now, there are three general classes of carbohydrates. We have monosaccharides, oligosaccharides, and polysaccharides. Now, monosaccharides are compounds that contain a single carbon group and two or more hydroxyl groups. They cannot be hydrolyzed to a simpler one. They have this general formula. But oligosaccharides, sugars linked by glycosidic bonds. Oligo from Greek, oligos means few. And polysaccharides, poly means in Greek many. Formed when many monosaccharides are bonded together through the loss of one water molecule for the formation of one single bond. Now, what are some of the functions of carbohydrates? They are major energy sources, like methane, glycogen in animals, and starch in plants. Also, oligosaccharides play a key role in processes that take place on the surface of cells, like methane cell-cell interactions and immune recognition. Whereas polysaccharides, they are essential structural components of several classes of organisms. For example, cellulose, cellulose, which are structural components of grass and trees, and chitin, methane, the major component of bacterial cell wall, as we will see. Now we start with the monosaccharides, which are the building blocks of all carbohydrates. They can be polyhydroxyaldehyde or polyhydroxyketones. We have two types, aldose and ketose. Aldose monosaccharides containing an aldehyde group. Example, glyceraldehyde. Ketose monosaccharide containing a ketone group. Example, dihydroxyacetone. Now, in the next figure, we will see the structure of some of these. And then again, monosaccharides could be trioses, tetroses, pentoses, hexoses, ectoses, etc. And we said the simplest are glyceraldehyde and dihydroxyacetone. These are trioses. Hexose sugars are the most abundant in nature, whereas pentose sugars are abundant in the structure of RNA and DNA. Tetrose and heptose sugars play roles in photosynthesis and other metabolic pathway. Let's start with the simplest trioses on like dihydroxyacetone. If we look at the structure of this compound, it does not contain chiral carbon, as you can see, so it does not exist in non-superimposable mirror image forms. Whereas if we look at the other one, the simplest carbohydrate that contain chiral carbon is called glyceraldehyde. Now, this carbon here in the middle is chiral because it is surrounded by four different groups. That's why it can exist in two forms that are mirror images of each other but non-superimposable. Now, the dashed wedges represents bond directed away from you, the viewer, and solid wedges are out of the plane of the paper. Now, we have two forms, D and L, and they differ in the position of the OH group. لاحظوا. When OH on the chiral carbon is to the right in dextro, it's D glyceraldehyde. When the OH group on the chiral carbon is to the left, it's levo, يعني L glyceraldehyde. Stereoisomerism in monosaccharides. Stereoisomers are molecules that differ from each other only in their configuration. What is configuration? Configuration refers to the three-dimensional arrangement of groups around the chiral carbon. Yani, this is what I explained before, the D and L. This is called configuration. Enantiomers, mirror image, non-superimposable stereoisomers. And the examples D and L glyceraldehyde. They are enantiomers of each other. Now, the possibility of stereoisomerism increases as the number of carbon atoms increase. The law 2 to the n, where n is the number of chiral carbon. So as n increases, the number of possible stereoisomers will also increase. Fischer projection. لاحظوا Fischer projection refers to a two-dimensional representation of the stereochemistry of three-dimensional molecules, whereas bonds are written in two-dimensional representation showing the configuration of tetrahedral stereocenters. فمثلا bonds written horizontally represents bond directed in front of the paper, whereas bonds written vertically represents bond directed behind the paper. So horizontal in front of paper and vertical behind the paper. And this Fischer projection method is after the German chemist Emil Fischer, who established the structures of many sugars. That's why it's called Fischer. And this is Fischer here, Fischer projection. Now, this is the structure for D-glucose. لاحظوا, it is an aldose. And here we have D-fructose, which is a ketose. Both of them are hexoses, but the difference is in the functional group. Now, the most highly oxidized carbon is written at the top and is designated number 1, and then you go all the way down. Now, we have how we determine that this sugar is a D or L configuration. We look at the chiral carbon with the largest number. And then we look at the OH. If it is to the right, then it is D. If it is to the left, it's OH. So as you see here, how many chiral carbons we have in D-glucose? 1, 2, 3, 4. Which one is the highest numbered chiral carbon? This one. We look, OH to the right, D. OH to the left, L. And this is the so-called configuration. Aldotetroses. Most common sugars are aldoses rather than ketoses. They contain two chiral carbons, carbon 2 and carbon 3, and 4 possible stereoisomers. 2 to the power 2, which is equal 4 possible stereoisomers. 2 of them have the D configuration and 2 have the L configuration. It's always like this. If a sugar has 50, for example, possible stereoisomers, 25 are in the D and 25 are in the L configuration. Then we come to the so-called diastereomers, which are non-superimposable, non-mirror image stereoisomers. For example, here, if we look at L-threose and L-erythrose. L-threose is the diastereomers of both D and L-erythrose, whereas L-erythrose is the diastereomer of both D, and I will show them to you. Let's first introduce this concept called epimers. Epimers, what are epimers? Stereoisomers that differ from each other in the configuration at only one chiral carbon. And an example of epimers is found here. D-erythrose and D-threose. Let's see. Although, of course, they are diastereomers because they are not mirror images of each other, and at the same time, they are epimers. Why? Because they differ in the configuration around this chiral carbon. لاحظوا here OH, right? Here OH left. And these are the same. Then we take the erythrose and its mirror image. They are called enantiomers. And then D-threose and L-threose, and also these are a pair of enantiomers. If you have an aldo pentose with 3 chiral carbons, which means we have 2 to the power 3, which means 8 possible stereoisomers, 4 D forms and 4 L forms, L-hexoses, etc. For example, D sugars rather than L sugars predominate in nature. Then for sugars, the D form predominates. Then we talked about this is the simplest triose, then tetrose, then these are pentoses, and then we have here hexoses, 6 carbon. If we take, for example, D-glucose and D-mannose, they are next to each other. Are they mirror images? No. So they are the stereomers. Now, are they epimers? We compare the configuration around chiral carbons. For example, carbon 2 here OH, right here OH left. So this is a difference. Whereas the remaining chiral carbon have the same configuration. So yes, we can say D-glucose and D-mannose are indeed epimers because they differ only in the configuration around carbon 2. Whereas D-glucose and D-galactose are also epimers because they differ in the configuration around carbon number 4 here. However, D-mannose and D-galactose are not epimers. Why? Because they differ in the configuration around 2 chiral carbons. Now, cyclic sugars with 5 or 6 membered rings. Now, sugars, especially those with 5 or 6 carbon atoms, exist as cyclic rather than open chain form. Cyclization of sugars take place because of interaction between functional groups at distant carbons, such as carbon 1 and carbon 5 to form cyclic hemiacetal in aldohexoses. So what is a hemiacetal? A compound that is formed by the reaction of an aldehyde with an alcohol. And when cyclization due to interaction between carbon 2 and carbon 5 results in hemiketal formation in ketohexoses. Then hemiketal is a compound that is formed by the reaction of a ketone with alcohol. Then aldehyde with alcohol بيعطيني hemiacetal and ketone with alcohol gives me hemiketal. Now in both cases the carbonyl carbon becomes a new chiral center called the anomeric carbon. Let's see how cyclization occurs. Now usually in organic chemistry reaction between alcohol and aldehyde give me hemiacetal. Now if the two function groups are on the same molecule, for example here reaction between carbon number 1 and the OH group of carbon number 5, the oxygen, you see reaction even between the oxygen here act as a nucleophile, attacks the carbonyl carbon, and since there is a free rotation around this aldehyde group, then we have two possibilities that OH, when cyclization occur, OH is down, as you can see, this will give me alpha D-glucose, and it could be also up, and this will give me beta D-glucose. So now these are called Haworth projection formulas, and these are Fischer projection formulas as we said. So alpha D-glucose in both representation as well as beta D-glucose. Now the newly formed carbon is chiral and is called the anomeric carbon number 1. It's usually given number 1 in counting. So the Fischer formula, D-glucose has 4 chiral centers. In the Haworth, D-glucose have 5 chiral carbons, remember. Now what is the relationship between alpha and beta, they are called anomers. So what are anomers? Are one of the possible stereoisomers formed when sugar assumes the cyclic form, designated alpha and beta. And here, this is alpha, this is beta. What is the relation between them? They are called anomers. Now, in the Haworth projection formulas, cyclic structures are shown in perspective drawings as planar 5 or 6 membered rings viewed nearly edge-on. لاحظوا في عندي furanose. These are cyclic sugar with a 5-membered ring. Rings are very nearly planar. And pyranose, cyclic form of a sugar containing 6-membered ring. And usually these exist in solution in the chair conformation. Again, we have here the designation beta means that OH on the anomeric carbon is cis to the terminal. And alpha means that it is trans. I will show this to you as we go. Then a 6-membered ring is called pyranose relative to compound called pyran, and the 5-membered ring furanose relative to compound called furan. And زي ما حكينا the Haworth is preferred by biochemists, and the chair conformation is preferred by organic chemists. Now again, let's look at the cyclization of a glucose another time. Even this is the Fischer Logo, and here we draw it in this way for cyclization to occur. Then oxygen will attack here, and 2 forms are possible. لاحظوا the alpha anomer and the beta anomer. لاحظوا OH and CH2OH here, they are in trans relation. So this is alpha. When OH and CH2OH in carbon 6 are in cis position, this produces the beta anomer. Then we have alpha, we have beta. And the 2 forms are possible, as I said, because aldehyde group has rotational freedom here around carbon 1, carbon 2 bond. That's why anomers are possible. And remember, alpha-D-glucose is the most prevalent in biochemistry. Again, cyclization. Now let's compare between Fischer, Haworth, and abbreviated Haworth here. This is the Fischer. لاحظوا any OH group that is right in the Fischer becomes down in Haworth, and any OH group that is left in Fischer becomes up in Haworth. Remember this. So all the groups here that are on the right, they become all down. You see, carbon 1, carbon 2, carbon 3 up, carbon 4 down, and so on. So this is, these are the alpha and beta D-glucose, as you can see in both Fischer and Haworth. Also, we have a 5-membered ring sugar called ribose. In Fischer, also in Haworth, OH left, up, beta D-ribose. And as we said, the ribose is important in the structure of DNA and RNA. What are some reactions of monosaccharides? Redox reactions of simple sugars. Oxidation and reduction reactions of sugars, they play key roles in biochemistry, as we will see. Oxidation of sugars provides energy for organisms to carry out their life processes, and the highest yield of energy from hydrocarbon occurs when sugars are completely oxidized to CO2 and water in aerobic processes. Now, several oxidation reactions of sugars are of some importance in in lab practice because they can be used to identify sugars. Aldehyde groups can be oxidized to give the carboxyl group. And that is characteristic of acids. And this reaction is the basis test for the presence of aldoses. It is a test for reducing sugar. لاحظوا aldoses are reducing sugars that contain the free carbonyl group and can react with an oxidizing agent. Okay, now oxidation of a cyclic hemiacetal form gives a lactone, which is a cyclic ester linking the carboxyl group and one of the sugar alcohols. لاحظوا we have two types of reagent used in the lab to detect the presence of reducing sugars. لاحظوا first is those Tollens reagent. هذا هو Tollens reagent which uses the silver ammonia complex AgNH3 by 2 plus as the oxidizing agent. And what results? A silver mirror is produced as we will see. إذن here زي ما حكينا Tollens reagent أيوه. If anomeric carbons are involved in a glycosidic linkage, the result will be negative in the Tollens reagent test. If another anomeric carbon is not bonded and it's free, the result will be positive. And free silver metal is deposited on the wall of the test tube, as you see here, as a result of the Ag plus in the complex being reduced to the free silver metal. This is called silver mirror, produced by an aldehyde. And this results after the addition of Tollens reagent to an aldehyde. And this is a positive test for reducing sugars. We can say that all monosaccharides and disaccharides are reducing sugars except sucrose, as we will see. Now, when the carbonyl group of a sugar لاحظوا in addition to oxidized sugar, there are some important reduced sugars. Reduced sugars, لاحظوا, like in this example here, a hydrogen atom is substituted for one of the hydroxyl groups of the sugar. In this compound called L-fucose, لاحظوا, which is found in the carbohydrate portion of some oligo. In some of found in oligosaccharides and in some glycoproteins, including the ABO blood group antigens. إذن لاحظوا the reference is beta L-galactose. Now, if you replace this oxygen with hydrogen, then it becomes, this is called a reduced sugar. And the same, if you have here ribose, and in position 2 here, you replace the oxygen with hydrogen, then you have, this is called a reduced sugar. So these two are examples of reduced sugars. In addition, لاحظوا when the carbonyl group of a sugar like مثلا D-sorbose is reduced to a hydroxyl group, the resulting compound is called alditol. فمثلا D-sorbose become D-sorbitol. لاحظوا. However, D-xylulose, if you reduce this carbonyl group, it becomes D-xylitol. And these are have commercial importance as sweeteners in sugarless chewing gum and candy. So these two, D-sorbitol and D-xylitol, are artificial sweeteners. Sugar esters and ethers. What are some important esterification reactions of sugars? Now, hydroxyl groups of sugars behave exactly like other alcohols. They can react with acids and derivatives of acids to form esters, phosphate esters. They are intermediates in the breakdown of carbohydrates to provide energy, as we will see, formed by transfer of a phosphate group from ATP to give the phosphorylated sugar ADP. You see here the formation of phosphate ester of glucose, then beta D glucose plus a molecule called ATP. By the way, ATP is the phosphate group donor. كمان مرة ATP is the phosphate group donor. The enzyme لاحظوا specifies the interaction with this CH2OH on carbon 6 with oxygen on carbon 6, and the enzyme is called hexokinase to form the beta D glucose 6-phosphate plus ADP. And when we talk about metabolism, we will see this reaction. Formation of a glycosidic bond. Now, what is a glycoside? It's a compound in which a compound formed when a hemiacetal carbon reacts with an alcohol to give a full acetal. Now, resulting bond is called a glycosidic bond. This is not an ether. No. Furanoside glycosides involving furanose يعني 5-member ring, while pyranoside glycosides involving a pyranose 6-member ring. If you look at this, an example of formation of a glycoside between a hemiacetal alpha D glucopyranose plus methyl alcohol to form this full acetal called methyl alpha D glucopyranoside. This is a glycoside, and this is the glycosidic bond. Then a glycosidic bond is a bond between a sugar and another molecule. Any bond between a sugar and another molecule is known as a glycoside. Now, the glycosidic bonds between monosaccharides units are the basis for the formation of oligosaccharides and polysaccharides. Remember this. Formation of glycosidic bonds. Now, as I said, these are the basis for the formation of oligosaccharides and polysaccharides. These glycosidic linkage take many forms. Now, anomeric carbon of one sugar can be bonded to any one of the OH groups on the second sugar to form an alpha or beta glycosidic linkage. لاحظوا here what is the notation of the linkage specifies anomeric form of the sugar that is involved in the bond and carbon atoms of the two sugars that are linked. As we will see, مثلا, two different disaccharides of alpha D glucose. لاحظوا here in this you see two different types of bonds here. لاحظوا this is carbon 1, 2, 3, 4 on this monosaccharide, and in this one it is one carbon 1 here, so the bond is 1, 4. Then the carbon between 1 and 4, and the type is alpha, so it's alpha 1,4 glycosidic bond. Now if the glycosidic bond between carbon 1 and carbon 6 here, so it's called alpha 1,6 glycosidic bond. And usually this glycosidic bond occurs at a branch point, the alpha 1,6. Another possibility of a glycosidic bond, this time between two beta D-glucose molecules. لاحظوا the bond is between carbon 1 and carbon 1, and its type is beta, so it's beta because both of them, and 1,1 glycosidic bond. So it is, لاحظوا, this is carbon 1 of this monosaccharide, and this is carbon 1 of this monosaccharide. So that's why its type is beta, so it's beta 1,1 linkage. As you can see. Now, variation in glycosidic linkage lead to the formation of linear and branch chain polymers. Now, if internal monosaccharide residues that are incorporated in a polysaccharide form only two glycosidic bonds, the polymer will be linear. Now, some internal residue can form three glycosidic bonds, leading to the formation of a branch chain structures. So let's look at this figure.
دكتور عشان بس باقي المحاضرة 4 دقائق وهيك، فيعني لو بآخر دقيقة تعطينا المجال نسأل.
ايش؟
دكتور عشان المحاضرة راح تخلص كمان 4 دقائق. لو في مجال نسأل بآخر دقيقتين.
على طول. هلا بعطيكم المجال. Okay, إذن هون if we look at this figure, this is the last figure we want to talk about. It shows us linear and branch chain polymers of alpha D glucose. Here notice that this is linear. All the types of linkages are alpha 1,4. So in linear forms we have alpha 1,4. لاحظوا the branch chain polymer occurs in amylopectin and glycogen, etc. لاحظوا the linear form, again all the glycosidic bonds are alpha 1,4. But when we want to make a branch, it becomes alpha 1,6. Then this is a branch point, this is a second branch point. So as you can see here, remember that always alpha 1,6 occur at branch point, whereas all other glycosidic bonds along the chain are of the type called alpha 1,4. Okay, let's keep the rest for questions.
دكتور امتحان المد راح يكون بتشابتر اللي عندي تشابتر 6 ولا كيف؟